So equilibrium constant is useful for determining extent of a reaction, because we know they never go to completion. So let's look at this example, ATP plus water to ADP plus a phosphate ion, plus we said this releases free energy. We know that delta G at standard state here is about negative 28 kilojoules per mole. I think before I said negative 30. The exact number depends on ion concentrations, such as magnesium. It depends on pH. This is Monday's conversation with acid-base, because pH is hydrogen ion concentration dependent. So just some other things, but it'll be roughly when we're talking about standard state in this sort of arena. And let's talk about exclusively the forward reaction now. So if we want to write the equilibrium constant for the forward reaction, we would have KEQ is equal to the concentration of ADP raised to the 1. These all are just have a 1 mole stoichiometric coefficient. Phosphate ions raised to the 1 over ATP and H2O. But one of the things I said is that we do not need to write this here, and you're not going to see it there anymore. And this is because all of these concentrations in the equilibrium constant are actually the concentration over the concentration at standard state. Okay. These are all 1 molar for others, so we just don't include the fact that dividing by 1 molar is on the bottom of all of these. For water, the top and bottom are both 55 molar. So it's just a 1 and it drops out. The concentration of water, what's the concentration of H2O over the concentration of H2O at standard state? Well, this is going to be 55 molar over 55 molar. We said all of this stuff is in the millimolar range, so we're really not affecting this ever. And we're always going to let this term be 1. So now that we sort of have thought this through, we have this information, which maybe we got from a calorimetry experiment. Let's calculate our equilibrium constant at 298 Kelvin. We'll let that be our standard state temp. So if we calculate the equilibrium constant for this reaction at 298, it will be KEQ is equal to E negative delta G over RT. This is equal to E to the negative 28,000 joules per mole, okay, divided by 8.314 joules per mole Kelvin is gas constant times 298 Kelvin. Okay, this will drop out, these will drop out. This is going to be equal to 28 over 2.478, or approximately 10 to the 5th. This is unitless. It should be unitless. KEQ is unitless. If it's not, maybe you missed something. Okay? So in living cells, the concentration of the phosphate ions is maintained at about 10 to the negative 2 molar. I'm telling you that this is true. How is it maintained? How can I maintain the concentration of phosphate ions inside my cell at 10 to the negative 2 molar all the time? Yes? what literally prevents things from going in and out of the cell physically? And what's in the membrane? So there's the membrane, and then there's some sort of pump or protein or something involved in letting transport happen, right? Membrane is going to stop it from going across, and when it needs to come in or out, depending on changes in concentration, some pump is there to let that happen. Okay. And so this is the concentration that your cells will be trying to maintain. So if you sort of plug these values in to our equilibrium constant, we have 10 to the 5th for KEQ. You can still see this. 10 to the 5th is here. The concentration of ADP divided by the concentration of ATP times about 10 to the -2 molar for the phosphate ion, which would mean this term here is about 10 to the 7th, which means that there is basically like 1 part ATP for every 10 million parts of ADP. Almost all ATP gets converted to ADP at equilibrium if we're at standard state. Or like I said, there's like 1 part per 10 million is ATP, and the rest would be ADP. That makes sense to us in that our sign for our delta G is very big and very negative, meaning the forward reaction wants to happen. So this is just another case. Now we're looking at glycerol 1-phosphate and water breaking down to glycerol and a phosphate ion. So the sign of delta G at standard state is smaller than 30. So just right now, before I put the math up, what do you sort of expect the ratio of glycerol to glycerol 1-phosphate to be compared to the 10 to the 7th I showed for ADP to ATP? It should be a smaller ratio. I do not expect to make as much glycerol. I do not expect to have as much completion of this reaction because it is not as favorable, it is not as negative of a change in free energy. Okay? So again, in this case, step 1, calculate the equilibrium constant using this information. Plug it all in. It's about 10 to the 1.6. Again, all of our cells are able to maintain our phosphate ion concentration at approximately 10 to the -2 molar. So now I have this relationship here, and I can spit out a ratio of closer to, rather than 10 to the 7th, about 4,000. This reaction proceeds to about 99.97% completion. The standard free energy change for the hydrolysis of glycerol 1-phosphate is not as favorable as the hydrolysis of ATP. It still gives me a source of energy that I could use for something. As standard free energy change becomes less negative, the equilibrium point will continue to move further away from completion for the forward reaction. The closer that value is to 0, the more likely that things are actually going back and forth all the time. And what we'll show for protein folding is that the change in free energy for folding a protein is negative. It is a spontaneous process. We know that proteins fold on their own, but it's a really small number such that the likelihood of a protein folding and unfolding regularly happens.